moment you began watching this video, the moment you finish it, and the exact moment you inhabit right now. According to the fundamental laws of physics, these three events exist simultaneously. We perceive time as a river that flows, a past that vanishes into nothingness, and a future that has yet to arrive. However, Einstein's general relativity and Minkowski's four-dimensional spacetime geometry whisper a vastly different reality. Time does not flow, time simply is. We are not victims of an inexorable current, but travelers within a gargantuan, four-dimensional block universe, merely scanning specific coordinates with the narrow beam of our consciousness. In this exploration, we will dismantle humanity's greatest illusion, time itself, examining its structure from the jittering uncertainty of subatomic particles to the crushing silence of a black hole's event horizon. Welcome to the architecture of eternity. Time is perhaps the most familiar yet most mysterious aspect of our existence. We experience it every moment of our lives, watching clocks tick forward, seasons change, and our own bodies age. We plan for the future, remember the past, and live in what we call the present. Yet when we try to define what time actually is, we find ourselves confronting one of the deepest puzzles in all of science and philosophy. What is time? Is it a fundamental feature of the universe, woven into the fabric of reality itself? Or is it merely a useful illusion, a construct of our consciousness that helps us make sense of change and causation? Does time flow like a river, carrying us inexorably from past to future? Or does it exist all at once, with past, present, and future equally real, and our sense of flow merely a trick of perception? These questions have occupied human minds for millennia. Ancient philosophers pondered whether time had a beginning or stretched infinitely into the past. They wondered whether the future was fixed or open, whether our choices mattered or were predetermined. Religious thinkers contemplated eternity and the relationship between time and the divine. Poets and artists have tried to capture time's passage, its weight, its fleeting nature, the way it seems to speed up or slow down depending on our experiences. But it is in the realm of physics that we have made the most startling discoveries about time's nature. Over the past century, our understanding of time has been revolutionized multiple times. We've learned that time is not the absolute, universal constant that common sense suggests. It can stretch and compress. It can be warped by gravity and motion. It is intimately connected with space in ways that defy our everyday intuition. At the quantum scale, time behaves in ways that seem to violate our most basic assumptions about causality and the flow from past to future. In this exploration, we'll journey through the major scientific theories that have shaped our modern understanding of time. We'll begin with Einstein's revolutionary insights about relativity, which showed that time is relative rather than absolute, that it can dilate and contract, that it is inseparable from space. We'll explore how gravity affects time, bending it around massive objects and bringing it nearly to a standstill at the edge of black holes. Then we'll turn to thermodynamics and entropy, investigating why time appears to have an arrow, always pointing from past to future, from order to disorder. We'll see how the second law of thermodynamics gives time its direction, and why we remember the past but not the future, why we see eggs break but never spontaneously reassemble, why the universe seems to be running down toward an eventual heat death. Next, We'll dive into the quantum realm, where time takes on even stranger properties. We'll examine how quantum mechanics treats time differently from other physical quantities, how measurement and observation seem to create the present moment, how entangled particles can appear to coordinate their behaviors across space instantaneously. We'll confront the measurement problem and the question of how the fuzzy quantum world gives rise to the definite classical world we experience. We'll then explore the black universe theory, also known as eternalism, which suggests that all moments of time exist equally, laid out in the form minus-dimensional spacetime. According to this view, the past does not cease to exist and the future already exists, our sensation of time flowing. The present moment being special is an illusion of consciousness. We'll examine the evidence for this counterintuitive perspective and its profound implications for free will, causation, and the nature of reality itself. Along the way, we'll encounter paradoxes and puzzles. Can time travel exist? If we could travel to the past, could we change it? What happens to causation when we allow closed time like curves? Why does quantum mechanics seem to conflict with general relativity when it comes to time? Can these two great theories be unified? And what would such a unification tell us about time's ultimate nature? Finally, we'll consider the frontiers of physics where researchers are working to resolve these tensions and deepen our understanding. String theory, loop quantum gravity, and other approaches to quantum gravity each have different implications for time's nature. Some theories suggest time might be emergent rather than fundamental, arising from more basic timeless physics. Others propose that space-time itself might be quantized with a discrete structure at the Planck scale. Through all of this, we'll see that time is far stranger and more subtle than our everyday experience suggests. The closer we look, the more mysterious it becomes. Yet each mystery solved and each question answered opens up new vistas of understanding, new ways of conceptualizing our place in the cosmos, new insights into the fundamental structure of reality. This journey through theories of time is not just an abstract intellectual exercise. Our understanding of time shapes how we think about ourselves, our choices, and our universe. It affects how we understand causation, free will, and determinism. It influences our sense of mortality and meaning. And it reveals the remarkable power of human reason to probe the deepest mysteries of existence, to test our intuitions against rigorous observation and mathematics, and to discover truths that are at once surprising and profound. So let us begin our exploration of time, that most familiar stranger, that ever-minus present mystery, that dimension we inhabit yet barely understand. Let us see what a century of physics has revealed about the nature of time, and what questions still remain unanswered. Before Einstein revolutionized our understanding of space and time, the dominant view of temporal reality came from Isaac Newton, whose laws of motion and universal gravitation had successfully described the physical world for more than 2 centuries. Newton's conception of time was elegant, intuitive, and seemingly self-evident. It matched our everyday experience and provided the foundation for classical mechanics. Yet it would prove to be, in important ways, wrong. Newton articulated his view of time in his masterwork, the Principia Mathematica, published in 1000, 687th, he wrote absolute true and mathematical time of itself, and from its own nature, flows equably without relation to anything external. This single sentence encapsulates the classical understanding that dominated physics until the early 20th century. What did it mean by absolute time? He meant that time exists independently of any observer, of any events, of any physical processes. It is not something that depends on where you are, how fast you're moving, or what you're doing. Time simply is, flowing uniformly throughout the universe at the same rate for everyone and everything. Whether you're on Earth or Mars, whether you're sitting still or moving at tremendous speed, whether anything is happening or not, time marches forward at the same steady pace. This conception had several important implications. First, it meant that simultaneity was absolute and universal. If two events happened at the same time according to one observer, they happened at the same time according to all observers, regardless of their location or motion. The idea that simultaneity might be relative, that two events could be simultaneous for one observer but not for another, would have seemed absurd. Second, it meant that there was a universal present moment that extended throughout the entire universe. At this very instant, there is something happening on Alpha Centauri, something happening in the Andromeda Galaxy, something happening at the edge of the observable universe, all occurring right now, all part of the same present moment. The past is absolutely past for everyone, the future absolutely future, and the present absolutely present. Third, it meant that time could be measured by clocks, and that ideal clocks anywhere in the universe, regardless of their construction or location, would tick at the same rate. Time was something that could be known objectively and precisely. The entire universe was coordinated by a single, universal clock. Newton's absolute time was intimately connected to his conception of absolute space. Just as time flowed uniformly everywhere, space existed as an absolute stage on which events unfolded. This space had a structure independent of the matter and energy within it. You could be moving or at rest relative to absolute space itself, even if there were nothing else in the universe to compare your motion to. This framework of absolute space and absolute time provided the foundation for Newtonian mechanics. Newton's laws of motion described how objects accelerated under forces, how momentum was conserved, how gravity worked. These laws were formulated in terms of positions in absolute space changing over absolute time. The mathematics was clear and the predictions were remarkably accurate. For more than 2 centuries, this framework served physics extraordinarily well. It successfully described planetary orbits, the motion of projectiles, the behavior of fluids, the workings of machines. Engineers used it to build bridges and engines. Astronomers used it to predict eclipses and the positions of planets. The success of Newtonian mechanics was so complete that many physicists in the late 19th century believed that the fundamental laws of physics were essentially understood, with only details remaining to be worked out. Yet there were hints that something was amiss. The study of electromagnetism, particularly the work of James Clerk Maxwell in the 1862, suggested that light traveled at a constant speed in all directions. This seemed to imply the existence of a medium for light waves, called the luminiferous ether, which would provide an absolute reference frame for motion. But experiments to detect Earth's motion through this ether, most famously the Michelson-Morley experiment of 1887, consistently failed to find it. Moreover, Maxwell's equations for electromagnetism had a curious property. Unlike Newton's laws, which looked the same in all inertial reference frames moving at constant velocity relative to each other, Maxwell's equations seemed to pick out a preferred reference frame in which the speed of light had its standard value. This suggested a deep tension between mechanics and electromagnetism, a tension that would ultimately require revolution in our understanding of space and time. The concept of absolute time also had philosophical difficulties, though these were less apparent at the time. If time exists independently of any physical process, what does it mean for time to flow? Flow implies change, but change relative to what? Time changing with respect to time itself is circular. And if time flows, how fast does it flow? 1 second per second is tautological and provides no real information. These questions, largely ignored during the era of Newtonian mechanics, success would become central to later philosophical discussions of time. But at the turn of the 20th century, the crisis in physics was not primarily philosophical, but empirical and theoretical. The inability to detect the ether, combined with subtle problems in understanding the behavior of light and electromagnetism, pointed toward something fundamentally incomplete in the classical picture. Nevertheless, Newton's absolute time represented a major intellectual achievement. He provided a clear, mathematically precise framework for understanding motion and change. It allowed physics to become a quantitative science capable of making accurate predictions. And it captured something important about our experience. Time does seem to flow uniformly, and events do seem to have an objective temporal order. The fact that this picture would need to be revised and revised dramatically does not diminish its historical importance. Classical mechanics remains an excellent approximation for everyday phenomena, for objects moving at speeds much less than the speed of light in regions where gravity is relatively weak. In these domains, Newton's absolute time works perfectly well. But as we'll see in the next sections, when we push through extreme conditions, very high speeds, very strong gravitational fields, very small quantum scales, the classical picture breaks down. Time proves to be far more flexible, far more intertwined with space, far more observer-dependent than Newton could have imagined. The revolutionary insights of Einstein and others would show that time is not absolute but relative, not independent but interconnected with the fabric of spacetime itself. In 1905, a 20-6-year-old patent clerk named Albert Einstein published a paper that would forever change our understanding of space and time. Titled On the Electrodynamics of Moving Bodies, this paper introduced what we now call special relativity, a theory that resolved the tensions in classical physics while overturning centuries of intuition about the nature of time. Einstein began with two simple postulates. First, the laws of physics are the same in all inertial reference frames, that is, in all frames moving at constant velocity relative to each other. This was already implicit in Newtonian mechanics, though Newton had also posited absolute space. Second, and more radically, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This second postulate was directly inspired by Maxwell's equations and the puzzling results of the Michelson-Morley experiment. But its implications were evolutionary. If the speed of light is constant for all observers, then something else must, given that something turned out to be our concepts of absolute space and absolute time. To understand why, consider a thought experiment. Imagine you're on a train moving at high speed, and you bounce a light beam off a mirror on the ceiling. From your perspective on the train, the light travels straight up and straight down, covering a distance of twice the height of the train car. But from the perspective of someone standing on the ground watching the train pass, the light follows a diagonal path, traveling both upward and forward with the train and then downward and forward, covering a greater distance. If the speed of light is the same for both observers, and the distance traveled is different, then the time elapsed must also be different. The person on the ground measures a longer time for the light's journey than you do on the train. Time itself runs at different rates for observers in relative motion. This phenomenon is called time dilation. The mathematics of special relativity makes this precise. If an observer at rest measures a time interval t between two events, an observer moving at velocity v will measure a time interval tt, 1 minus vc, where c is the speed of light. The factor 1 minus vc, called the Lorentz factor, describes how much time dilates. For everyday velocities, vc is minuscule, so is very close to 1, and time dilation is negligible. This is why we don't notice these effects in daily life. But as velocity approaches the speed of light, grows dramatically. At 90% of light speed is about to 0.3, meaning time runs more than twice as fast for the stationary observer compared to the moving one. As velocity approaches c approaches infinity, time would effectively stop for an object moving at light speed, which is one reason why massive objects cannot reach this speed. Time dilation has been confirmed by countless experiments. Atomic clocks flown on airplanes run slower than clocks on the ground by exactly the amount predicted by relativity. Particles called moons, created in Earth's upper atmosphere by cosmic rays, decay much more slowly when moving at high speeds than when at rest, allowing them to reach the surface before decaying despite their short lifetimes. GPS satellites must account for relativistic time dilation, or their positioning data would be off by kilometers. The famous wind paradox illustrates time dilation dramatically. Imagine winds, one of whom stays on Earth while the other travels to a distant star and back at near minus light speed. For the traveling twin, the journey might take 10 years. But due to time dilation, decades or even centuries might pass on Earth. When the traveling twin returns, they find their twin has aged much more, perhaps even died long ago. This is not a paradox in the sense of a logical contradiction, it's a real prediction of relativity, and one that has been verified experimentally with atomic clocks. But time dilation is just the beginning. Special relativity also reveals that simultaneity is relative. Events that are simultaneous in one reference frame are not simultaneous in another frame moving relative to it. This demolishes Newton's concept of a universal present moment extending throughout the universe. Consider two lightning strikes that an observer at rest judges to be simultaneous. Now imagine another observer moving at high speed. This observer will find that one strike occurred before the other. Crucially, both observers are correct. There is no absolute fact about whether the strikes were simultaneous. Simultaneity depends on the observer's state of motion. This relativity of simultaneity has profound implications. It means there is no universal now, no moment that is unambiguously the present throughout the universe. Different observers partition spacetime into past, present, and future in different ways, and no partition is more correct than any other. Special relativity also unifies space and time into a single entity called spacetime. In Newtonian physics, space and time were separate three dimensions of space and one dimension of time. But in relativity, they are mixed. What one observer perceives as a purely spatial separation, another observer in relative motion perceives as a combination of spatial and temporal separation. Space and time are not independent but are different aspects of a four-dimensional continuum. This four-dimensional space-time is described by the mathematics of Minkowski space, named after Hermann Minkowski, Einstein's former teacher. In Minkowski space, events are represented as points with four coordinates, three spatial and one temporal. The separation between events is given not by separate spatial and temporal distances, but by a spacetime interval that combines both. One of the most surprising aspects of special relativity is that different observers disagree not just about time, but about the order of events. For events that are far apart in space and close together in time, the order can be observer-dependent. One observer might see event A happen before event B, while another observer in relative motion sees B before A. However, causality is protected for events that can be causally connected where a signal traveling at light speed could connect them. All observers agree on the temporal order. This brings us to another revolutionary aspect of relativity. Nothing can travel faster than light. The speed of light is not just the speed of light, it's the maximum speed at which any information or influence can propagate through space. This cosmic speed limit is built into the structure of space-time itself. Why is there a speed limit? The mathematics of the Lorentz transformation shows that as an object's velocity approaches c, its mass effectively becomes infinite, requiring infinite energy to accelerate further. Moreover, if something could travel faster than light, it would be possible to construct scenarios that violate causality, allowing effects to precede their causes. The constancy of the speed of light also explains why we cannot simply add velocities in the classical way. If you're on a train moving at 100 mph and you throw a ball forward at 50 mph, classically, we'd say the ball moves at 150 mph relative to the ground. But if you're on a spaceship moving at 90% of light speed and you shine a flashlight forward, the light does not travel at 190% of light speed. It travels at exactly c as measured by any observer. Velocities must be combined using the relativistic velocity addition formula, which ensures the speed of light is never exceeding. All of these strange effects, time dilation, length contraction, moving objects are measured to be shorter along their direction of motion. Relativity of simultaneity, the constancy of light speed are not separate phenomena, but different manifestations of the unified geometry of spacetime. They all follow from Einstein's simple postulates and the requirement that the laws of physics be consistent. Perhaps the most famous consequence of special relativity is the equivalence of mass and energy, expressed in Einstein's equation E. This equation reveals that mass and energy are interconvertible, that mass is a form of stored energy. The enormous factor of C means that even a small amount of mass corresponds to a tremendous amount of energy, which is why nuclear reactions can release such vast amounts of power. Special relativity applies to inertial reference frames, those moving at constant velocity. It successfully describes the behavior of objects moving at high speeds in the absence of strong gravitational fields. But gravity presented a challenge. Gravity causes acceleration, taking us out of the realm of inertial frames. Moreover, Newtonian gravity acted instantaneously across distances, violating the speed minus of minus light limit. Einstein spent the next 10 years developing a theory that would incorporate gravity into the relativistic framework. The result, general relativity, would prove even more revolutionary, showing that gravity is not a force in the traditional sense but a manifestation of spacetime curvature, and that time is even more flexible than special relativity suggested. In 1915, Albert Einstein completed one of the greatest intellectual achievements in human history, the general theory of relativity. While special relativity had shown that time and space are relative and intertwined, general relativity went further, revealing that space-time itself is dynamic, capable of bending and warping in response to matter and energy. And in these curves of space-time, time itself flows at different rates depending on the strength of gravity. The key insight behind general relativity came from what Einstein called the happiest thought of my life. He realized that a person in free fall doesn't feel their own weight. An astronaut orbiting Earth is in free fall, continuously falling toward the planet, but also moving forward fast enough that they keep missing it. From the astronaut's perspective, they are weightless, floating freely. Conversely, a person standing on Earth's surface feels weight because the ground prevents them from following their natural path through space-time. This led Einstein to the equivalence principle. The effects of gravity are locally indistinguishable from the effects of acceleration. Imagine you're in an elevator in deep space, far from any gravitational source. If the elevator accelerates upward, you'll feel pressed to the floor, just as you do on Earth. You couldn't perform any experiment confined to the elevator that would tell you whether you were accelerating in space or sitting in a gravitational field. From this principle, Einstein derived a revolutionary conclusion: gravity is not a force pulling objects together, as Newton believed. Instead, gravity is the curvature of space-time itself. Massive objects like stars and planets create curved valleys and wells in the fabric of space-time, and other objects follow the straightest possible paths through this curved geometry. What we perceive as the force of gravity is actually objects following the geometry of curved space-time. To visualize this, imagine a rubber sheet stretched flat. Place a bowling ball in the center, and it creates a depression. Now roll a marble nearby. Instead of moving in a straight line, the marble curves toward the bowling ball, circling it or eventually falling into the depression. This is analogous to how planets orbit the sun. They're following the curvature of space-time created by the sun's mass. But this is where time becomes truly remarkable. Space-time curvature doesn't just affect spatial paths, it affects time itself. Clocks run slower in stronger gravitational fields. This phenomenon, called gravitational time dilation, means that time passes more slowly the closer you are to a massive object. The mathematics of general relativity, encoded in the Einstein field equations, makes this precise. The equations relate the curvature of spacetime described by the Riemann curvature tensor to the distribution of matter and energy described by the stress minus energy tensor. Solving these equations for various configurations of matter reveals how spacetime curves and, consequently, how time flows. Near Earth's surface, gravitational time dilation is tiny but measurable. A clock at sea level runs about 100 nanoseconds per day slower than a clock on a mountain top. This might seem negligible, but it's crucial for GPS satellites, which orbit at high altitudes where gravity is weaker. The satellite's clocks run about 45 microseconds per day faster than clocks on the ground. Combined with the special relativistic effect of their orbital velocity, which makes their clocks run slower, the net effect is about 38 microseconds per day. Without correcting for this, GPS positioning would drift by about 10 kilometers per day. The effect becomes more dramatic near more massive objects. At the surface of a neutron star, one of the densest objects in the universe, time runs about 30% slower than it does in free space far from any gravitational source. An observer far from the neutron star watching someone on its surface would see them moving in slow motion, their processes running significantly slower than normal. The most extreme case is a black hole. At the event horizon of a black hole, time from the perspective of a distant observer appears to slow to a complete stop. If you watched someone fall toward a black hole, you would see them slow down as they approach the event horizon, becoming redder due to gravitational redshift and dimmer, but never quite crossing it. From the perspective of the falling person, however, they would cross the event horizon in a finite time and continue falling toward the singularity. This dramatic difference in experience time is one of the most striking predictions of general relativity. The slowing of time in gravitational fields has another consequence: gravitational redshift. Light climbing out of a gravitational well loses energy, and since a photon's energy is proportional to its frequency, the light's frequency decreases, it becomes redder. This effect has been measured in laboratories on Earth and observed in the light from white dwarf stars and other compact objects. General relativity also predicts the existence of gravitational waves ripples in spacetime itself that propagate at the speed of light. When massive objects like black holes or neutron stars orbit each other and eventually merge, they create violent disturbances in spacetime that spread outward like ripples on a pond. These waves were first directly detected in 2015 by the LIGO experiment, confirming yet another prediction of Einstein's theory and opening a new way to observe the universe. The warping of spacetime by matter creates what we might call gravitational potential wells. The deeper you are in such a well, the more slowly time passes. You can think of the universe as filled with these wells of varying depths, centered on planets, stars, galaxies, and clusters of galaxies. Time flows at slightly different rates throughout this landscape of curved spacetime. This has a fascinating implication: your biological aging, the ticking of clocks. All physical processes depend not just on your intrinsic properties, but on where you are in spacetime. Two identical clocks, one in deep space and one on Earth, will record different amounts of elapsed time. Neither is more correct; they're both measuring time accurately in their locations. Time itself is not a universal, flowing substance but a dimension that can be stretched and compressed by the presence of matter and energy. General relativity also allows for exotic solutions to the Einstein field equations that have strange temporal properties. Some solutions contain closed time, like curved paths through spacetime that loop back on themselves in time, potentially allowing time travel to the past. These include rotating black holes described by the Kermetric, traversable wormholes, and spacetimes with strange topologies. Whether such solutions exist in nature, and if they do, whether they permit time travel without paradox, remains an open question. One of the most successful predictions of general relativity is the observed precession of Mercury's orbit. Newton's theory of gravity couldn't fully explain why Mercury's elliptical orbit slowly rotates over time. General relativity provided the missing piece, accounting for the extra precession with remarkable precision. Similarly, gravitational lensing, the bending of light by massive objects, has been observed countless times, from Einstein's rings to the magnification of distant galaxies by foreground galaxy clusters. The expansion of the universe itself is a prediction of general relativity. When Einstein first applied his equations to the universe as a whole, he found they predicted a dynamic universe, either expanding or contracting. This so troubled him at the time. The universe was believed to be static that he introduced a cosmological constant to stabilize his solutions. When Edwin Hubble discovered in 1929 that distant galaxies are receding from us, revealing the universe's expansion, Einstein reportedly called the cosmological constant his biggest blunder. Ironically, modern observations suggest that a cosmological constant, or something like it, called dark energy, does exist and is causing the universe's expansion to accelerate. The expanding universe gives time a cosmic significance. There is a cosmic time coordinate that measures the age of the universe since the Big Bang, currently about 13.8 billion years. While this might seem to restore a kind of absolute time, it's more subtle than Newton's version. Cosmic time is defined by observers who see the universe as homogeneous and isotropic, the same in all directions. For observers moving at high speeds relative to this cosmic rest frame, or in regions of strong space-time curvature, time would flow differently. General relativity reveals that time is not just relative to velocity, as special relativity showed, but also to position in a gravitational field. The stronger the gravity, the slower time flows. This means that if we could somehow survive at the event horizon of a black hole and then return to Earth, we would find that billions of years had passed on Earth during what seemed like a much shorter time to us. The science fiction concept of time dilation is not fiction, it's a real, measured phenomenon. Yet general relativity, for all its success, has limitations. It breaks down at singularities, points of infinite density like the center of black holes or the initial moment of the Big Bang. At these points, the equations produce infinities and cease to make sense. Most physicists believe this indicates not that infinities actually exist in nature, but that general relativity is incomplete, that it needs to be merged with quantum mechanics to describe these extreme conditions. The quest for such a theory of quantum gravity remains one of the great challenges of theoretical physics. While relativity reveals that time is flexible and observer-minus dependent, it doesn't explain one of time's most obvious features, its apparent direction. We remember the past but not the future. Eggs! but don't spontaneously reassemble. Heat flows from hot to cold, never the reverse. The universe seems to be running down, becoming more disordered as time progresses. This asymmetry, the sense that time has an arrow pointing from past to future, is not addressed by relativity, which treats past and future symmetrically. To understand the arrow of time, we must turn to thermodynamics. The second law of thermodynamics states that the entropy of an isolated system never decreases over time. Entropy is often described as disorder, though more precisely it measures the number of microscopic configurations that correspond to a system's macroscopic state. A system with high entropy has many possible microscopic arrangements that look the same at the microscopic level, while a system with low entropy has relatively few such arrangements. Consider a room with all the air molecules in one corner. This is a low minus entropy state because there are relatively few arrangements of molecules that would keep them all in one corner. Now let the molecules spread out to fill the room. This is a high minus entropy state because there are vastly many arrangements of molecules that would appear as a uniform gas filling the space. The second law says that isolated systems naturally evolve from low minus entropy to high minus entropy states. Why? The answer lies in probability. If a system can be in many different microscopic states that all look similar microscopically, it's overwhelmingly likely to be in one of those states simply by chance. A room with air spread throughout has far more possible molecular arrangements than a room with air in one corner. So if molecules are moving randomly, the system will almost certainly end up with air spread throughout. This probabilistic interpretation of the second law was developed by Ludwig Boltzmann in the late 19th century. Boltzmann showed that entropy is related to the logarithm of the number of microstates Sk lane W, where S is entropy, K is Boltzmann's constant, and W is the number of possible microstates. This equation, engraved on Boltzmann's tombstone, connects the macroscopic concept of entropy to the microscopic world of atoms and molecules. The second law explains many irreversible processes. When you mix hot and cold water, they reach an intermediate temperature and never spontaneously separate into hot and cold again. When you break a glass, it doesn't spontaneously reassemble. When you shuffle a deck of cards, it doesn't spontaneously return to its original order. All these processes involve increases in entropy, moving from special, low minus entropy configurations to generic, high minus entropy ones. This gives time its arrow. Processes that increase entropy define a direction in time. We can tell past from future by noting which direction entropy increases. The past is the direction of lower entropy. The future is the direction of higher entropy. This thermodynamic arrow of time explains our subjective sense that time flows from past to future. But this raises a profound puzzle. If the fundamental laws of physics are time minus symmetric, they work the same whether time runs forward or backward. How can there be an arrow of time at all? Newton's laws, Maxwell's equations, the Schrödinger equation of quantum mechanics, and even Einstein's equations of general relativity are all time minus reversible. If you filmed a movie of particles obeying these laws and played it backward, you'd see particles still obeying the same laws. The resolution lies in the initial conditions. The laws of physics themselves don't determine the arrow of time the initial state of the universe does. The universe began in an extraordinarily low minus entropy state in the Big Bang. The early universe was smooth and homogeneous, with matter and energy distributed very uniformly. This might sound like a high minus entropy state, but it's not. Gravity makes uniformity a low minus entropy configuration because gravity is attractive. It wants to pull things together into clumps. From this special initial state, the universe has been evolving toward higher entropy ever since. Stars form from gas. Nuclear fusion converts hydrogen to heavier elements. Black holes form and eventually evaporate. And the universe expands and cools. All these processes increase total entropy, even though locally entropy can decrease as when stars for more life develops, because the overall system, the universe, increases in entropy. This explains the arrow of time, but it also creates what's known as the past hypothesis problem. Why did the universe begin in such a low minus entropy state? This seems to require incredibly special initial conditions at the Big Bang. Some cosmologists suggest this might be explained by inflationary cosmology, which proposes a period of rapid expansion in the universe's first moments. Others propose that our universe might be part of a larger multiverse, where different regions have different entropy configurations. And we necessarily find ourselves in a region where entropy is increasing because only such regions permit the existence of observers. The second law also explains our psychological arrow of time, where we remember the past but not the future. Memory formation involves creating records, physical structures in our brains that encode information. Creating these records necessarily increases entropy overall, even though the record itself might be relatively ordered. The direction in which we can form memories is thus determined by the direction of entropy increase, which is why we remember the past and not the future. Interestingly, the second law is statistical, not absolute. It's theoretically possible for entropy to decrease in a small system for a brief time, just extremely unlikely. If you watch a movie of molecules in a box and see them all gather in one corner, you'd know the movie is probably being played backward. But there's a tiny probability that the molecules could spontaneously all move to one corner, even with the movie playing forward. This is called a Boltzmann fluctuation, after Leonard Boltzmann. Boltzmann himself considered an even more radical possibility. What if our entire observable universe, with all its structure and low entropy, is just a random fluctuation from a state of maximum entropy? This Boltzmann brain problem has troubled cosmologists. The idea is that in an infinite universe at thermal equilibrium, random fluctuations will occasionally create regions of low entropy, including conscious observers. But the most probable way to create a conscious observer through fluctuation would be to create just the observer and their immediate memories, not an entire consistent universe with a long history. This seems to lead to a reductio ad absurdum. If the fluctuation hypothesis were true, we should expect to be disembodied brains with false memories rather than beings in a real universe. The resolution might be that our universe is not a fluctuation, but genuinely started from a low minus entropy Big Bang. But this raises the question of what mechanism set those initial conditions. Some theories propose that the universe's low minus entropy start is explained by quantum cosmology, or by the universe being part of a cyclical model where contractions restore low entropy. Another puzzle involves black holes. When matter falls into a black hole, it seems to disappear from the universe, and with it all information about its configuration. This appears to violate the second law, as the entropy of the external universe has decreased. However, Jacob Bekenstein and Stephen Hawking showed that black holes themselves have entropy, proportional to the area of their event horizons. When matter falls in, the black hole's entropy increases by more than the entropy lost from the external universe, preserving the second law. Hawking further showed that black holes emit thermal radiation and eventually evaporate completely. This Hawking radiation has a temperature inversely proportional to the black hole's mass. The evaporation of black holes creates what's known as the black hole information paradox. If a black hole evaporates completely, what happens to the information about all the matter that fell in? Does it disappear, violating quantum mechanics' requirement that information is preserved? Or is it somehow encoded in the radiation? And if so, how? This paradox connects the thermodynamic arrow of time to deep questions in quantum mechanics and quantum gravity. Resolving it might require understanding how information is encoded in the structure of spacetime itself, or how quantum effects modify the behavior of black holes at microscopic scales. The ultimate fate of the universe, according to the second law, is heat death, a state of maximum entropy, where no more useful work can be extracted, where everything has reached uniform temperature, and where no organized structures remain. In this far future, after all stars have burned out, all black holes have evaporated, and all matter has decayed or been dispersed, the universe would be a cold, dark, nearly uniform sea of radiation and elementary particles. Time would still exist in the sense that change would still occur, but the changes would be random fluctuations with no preferred direction. However, cosmological observations suggest our universe's expansion is accelerating due to dark energy. If this continues, the universe will expand forever, becoming ever more dilute and approaching absolute zero temperature. This big freeze scenario is the heat death carried to its logical conclusion. Alternatively, if dark energy behaves differently in the future, other scenarios like the Big Rip, where expansion accelerates until it tears apart all structures, or the Big Crunch, where expansion reverses into contraction, might occur. The thermodynamic arrow of time is thus intimately connected to cosmology. The fact that we see entropy increasing tells us something profound about the universe's history. It started in a very special, low-minus entropy state and has been evolving toward higher entropy ever since. This gives time its direction and explains why we experience it as flowing from past to future. Without this asymmetry, without the universe starting from low entropy, there would be no arrow of time, no clear distinction between past and future, and arguably no possibility of life or consciousness as we know them. When we descend from the realm of everyday objects to the quantum world of atoms and subatomic particles, time takes on yet more peculiar properties. Quantum mechanics, the theory that governs the microscopic world, treats time in a way that's fundamentally different from how it treats space and other physical quantities. This difference creates conceptual puzzles that remain unresolved to this day, and suggests that our understanding of time at the deepest levels is still incomplete. In classical physics, whether Newtonian or relativistic, time is a parameter that labels when events occur. It's external to the system being described, a backdrop against which physical processes unfold. In quantum mechanics, this treatment of time persists, but with strange consequences. While quantum mechanics describes how systems evolve in time, time itself is not treated as a quantum observable. It's not subject to the uncertainty principle in the same way that position, momentum, energy, and other quantities are. The Schrödinger equation, a fundamental equation of quantum mechanics, describes how a quantum system's wave function evolves over time. The wave function x t gives the probability amplitude for finding a particle at position x at time t. The equation is ith, whereas the reduced Planck constant in h is the Hamiltonian operator representing the system's total energy. This equation is deterministic given a wave function at one time. It precisely determines the wave function at all future times. Here's where things get strange. Before measurement, a quantum particle doesn't have definite properties. It exists in a superposition of multiple possible states simultaneously. An electron might be in a superposition of being in many different locations at once, with different probability amplitudes for each. Only when we measure the electron's position does it collapse into a definite location. This is the famous measurement problem of quantum mechanics. What role does time play in measurement? When exactly does the collapse occur? The Schrödinger equation describes smooth, continuous evolution, but collapse seems to be an instantaneous, discontinuous process. This is sometimes called the time of measurement problem. If collapse takes no time, it seems to violate the continuous evolution prescribed by quantum mechanics. If it takes some finite time, during what interval does it occur? And what determines this interval? Moreover, the measurement problem interacts strangely with relativity's lessons about simultaneity. If measurement collapses instantaneous with respect to what? Different observers in relative motion have different concepts of simultaneity. An event that is instantaneous for one observer extends over time for another. This creates tension between quantum mechanics and special relativity. Quantum entanglement deepens the puzzle. When two particles are entangled, measuring one instantaneously affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, seems to violate special relativity's prohibition on faster minus than minus light signaling. The resolution is that you cannot use entanglement to send information faster than light. The correlations between entangled particles only become apparent when you compare measurement results, which requires classical communication at or below light speed. Nevertheless, the correlations themselves seem to be established instantaneously, which is difficult to reconcile with relativistic notions of time. The uncertainty principle, ET2, relates energy and time, but time appears here in a different way than position appears in the position minus momentum uncertainty relation. In the energy minus time uncertainty relation, T represents the time over which the system evolves appreciably, not an intrinsic uncertainty in the time coordinate itself. There is no time operator in standard quantum mechanics analogous to the position or momentum operators. Time remains a classical parameter. This asymmetric treatment of time has troubled physicists since quantum mechanics was developed. Why should time be special? Some interpret this as evidence that time is indeed fundamentally different from space, that it plays a special role in the basic structure of reality. Others see it as a sign that quantum mechanics is incomplete, that a deeper theory would treat time and space on equal footing, perhaps quantizing time itself. The problem becomes more acute when we try to combine quantum mechanics with general relativity. In general relativity, time is part of the dynamic fabric of spacetime, curving and warping with matter and energy. In quantum mechanics, time is an external parameter. How can we have a theory where time is both an external parameter as in quantum mechanics and a dynamic variable as in general relativity? This is called the problem of time in quantum gravity, and it's one of the most vexing issues in theoretical physics. In canonical quantum gravity approaches like loop quantum gravity, when you try to write down the quantum version of Einstein's equations, you get what's called the Wheeler minus DeWitt equation. This equation describes the wave function of the entire universe, and remarkably, it contains no time parameter at all. It's a timeless equation, suggesting that the universe's quantum state doesn't evolve in time because time itself is part of what's being quantized. How can we reconcile this timeless picture with our experience of time passing? One approach is to suggest that time is emergent, it arises from something more fundamental. Perhaps what we call time is actually a measure of change in correlations between different parts of the universe. From an external, God's-eye perspective, the universe might be timeless, described by a static wave function. But from the perspective of observers inside the universe, comparing one part of the universe to another, it would appear that time passes. Another quantum puzzle involves causality. In the microscopic world, causes precede effects, and this ordering is preserved in relativity for causally connected events. But in quantum mechanics, the situation is murkier. Quantum field theory allows for virtual particles that can briefly violate energy conservation due to the uncertainty principle, appearing and disappearing in fleeting instants. Some interpretations of quantum mechanics, particularly transcational interpretations, suggest that quantum events involve both forward minus in minus time and backward minus in minus time and backward minus in minus time influences that cancel out to produce what we observe. Experiments have even demonstrated what seems like retrocausality in quantum systems. In delayed minus choice experiments, a decision made by an experimenter after a photon is passed through an apparatus seems to retroactively determine what state the photon was in when it passed through. These experiments don't allow through time travel or sending information to the past, but they do suggest that quantum mechanics doesn't neatly partition events into cause and effect the way classical physics does. The many minus worlds interpretation of quantum mechanics, proposed by Hugh Everett, offers a different perspective on quantum time. In this view, there is no measurement collapse. Instead, every quantum measurement causes the universe to branch into multiple parallel worlds, one for each possible outcome. Time evolution is thus not the collapse of possibilities into a single actuality, but the continuous branching of the universe into ever more numerous parallel timelines. This preserves the deterministic evolution of the Schrödinger equation, but at the cost of an enormous multiplication of worlds. Quantum mechanics also affects our understanding of the early universe. In the first moments after the Big Bang, the universe was so small and so dense that quantum effects were crucial. Quantum cosmology attempts to describe the Big Bang itself as a quantum event, Some proposals, like Hartle and Hawking's no minus boundary proposal, suggest that time itself might have emerged from a quantum state where the distinction between time and space breaks down. In this view, asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because time itself began with the Big Bang. Quantum decoherence provides insight into how the classical world emerges from quantum mechanics. When a quantum system interacts with its environment, interference between different quantum states is rapidly suppressed, making the system appear classical. This process happens quickly for macroscopic objects, but slowly for isolated microscopic systems. Decoherence thus provides an arrow of time a direction, in which quantum systems become classical. This decoherence arrow might be related to the thermodynamic arrow, as both involve increasing entropy and information loss. At the Planck scale, about 10⁻35 meters in 10⁻43 seconds, quantum effects on spacetime itself become important. At this scale, spacetime might not be smooth, but instead have a foamy, probabilistic structure, with tiny wormholes and fluctuations, constantly appearing and disappearing. Time at this scale might be fundamentally discrete, broken into indivisible Planck time units, rather than continuous. This would represent a quantum limit to the divisibility of time, just as atoms represent a limit to the divisibility of matter. Some approaches to quantum gravity, particularly loop quantum gravity, suggest that spacetime is indeed quantas built from discrete units. In this view, time is not infinitely divisible, but comes in minimum chunks. However, other approaches, like string theory, typically treat space-time as continuous, even at very small scales, though it might have extra dimensions beyond the four we experience. The relationship between quantum mechanics and time remains one of the deepest unsolved problems in physics. Why is time treated differently from space in quantum theory? Is this asymmetry fundamental, or does it point to a deeper theory? How do we reconcile quantum mechanics' external time parameter with general relativity's dynamic spacetime? Can we make sense of quantum cosmology and the universe's wave function? These questions sit at the frontier of theoretical physics, waiting for new insights that might revolutionize our understanding yet again. One of the most philosophically radical implications of relativity is the block universe theory, also known as eternalism. This view holds that past, present, and future all exist equally, that time is laid out like space, with all moments of time existing simultaneously in a 4-dimensional spacetime. Our sensation of time flowing and the present moment being special is, in this view, an illusion of consciousness rather than a feature of objective reality. The block universe interpretation emerges naturally from the mathematics of special and general relativity. In Minkowski's spacetime, the relativistic arena where events occur past, present, and future are not absolute categories. Due to the relativity of simultaneity, different observers disagree about which events are happening now. If your now includes events that are in someone else's past or future, then it seems that all moments must exist on equal footing. There is no universal present moment slicing through space-time. Instead, each observer has their own present, and these presents don't align. Imagine space-time as a loaf of bread. Each slice represents a moment in time, containing all of space at that instant. In Newtonian physics, there's a unique way to slice the loaf. Everyone agrees on how to divide spacetime into past, present, and future. But in relativity, different observers moving at different velocities slice the loaf differently. What's one person's now minus slice is tilted relative to another person's. If we draw lines of simultaneity for different observers, they cross each other, including events from what others would call past or future in their present. This suggests that rather than thinking of only the present as real with the past gone and the future yet to come, we should think of all of space-time as a fixed, or minus-dimensional structure. From this bird's eye view, the universe is a block containing all events that ever happened laid out in space-time like a completed movie film. Your birth, your reading this sentence, and your death are all equally real, all existing as events at different space-time coordinates. In the block universe view, nothing truly becomes or ceases to be. When we say something happened in the past, we mean it exists at an earlier time coordinate. When we say something will happen in the future, we mean it exists at a later time coordinate. But both past and future events exist just as much as present events do. You at age 5 didn't cease to exist. That version of you still exists at the space-time location corresponding to your 5th year. Similarly, you at age 80, if you live that long, already exists at the future space-time location. This might seem to contradict our direct experience. We feel the present moment is special, that it's uniquely real. We feel time flowing, carrying us from past to future. The block universe theory says this feeling, however vivid, is a feature of our consciousness, not of reality itself. Just as our eyes show us a 3 dimensional world, even though we're really seeing 2 dimensional retinal images that our brains interpret, our consciousness presents us with a sense of flow, even though reality is a static from dimensional structure. Why do we experience a flow of time if none exists? One answer involves memory and causation. Our brains record information about earlier time coordinates, but not later ones. We have memories of the past, but not the future, because causation runs in the direction of increasing entropy. This asymmetry, combined with the structure of consciousness, creates the subjective impression that time flows. The physicist Carlo Rovelli has suggested that the flow of time is like the concept of up. Ask someone where up is, and they'll point toward the sky. But up isn't a fundamental direction in space, it's just the direction away from Earth's center. A direction that's special because of our location and perspective. Similarly, the direction from past to future isn't fundamental to time itself, but is special because of the entropy gradient and our position within it. The block universe theory has profound implications for free will and determinism. If the future already exists in the block, then all our future actions are already laid out. This seems to threaten free will. If tomorrow's choices already exist at tomorrow's space-time coordinates, how can we truly be free to make them? Defenders of eternalism argue that free will is compatible with the block universe. Even if your future decisions exist, they're still your decisions, determined by your character, values, and reasoning at the time you make them. The fact that they exist in the block doesn't mean they're predetermined by anything external to you. Others find this unsatisfying and argue for alternative views of time. Presentism holds that only the present moment exists, the past no longer exists, and the future doesn't exist yet. This preserves our intuitive sense of time but faces difficulties in relativity, where there's no universal present. Post-BDSM, or the growing block universe theory offers a middle ground. The past and present exist, but the future does not yet exist and is genuinely open. This preserves an objective distinction between the fixed past and the open future, while allowing for the reality of temporal passage. Another variant is the moving spotlight theory. This accepts that all moments exist in the block, but adds that there's a special spotlight of nowness that moves through the block, making each moment present in turn. The spotlight is not part of physics, but is perhaps a metaphysical addition, something that picks out which moment is objectively present. Evidence for the block universe comes primarily from relativity's demonstrated accuracy. The relativity of sentientality isn't just a theoretical curiosity, it's been confirmed by countless experiments. GPS satellites, particle accelerators, and cosmological observations all verify that sentientality is relative. If sentientality is relative, then the distinction between past, present, and future cannot be absolute. This strongly suggests that all moments exist equally. However, some philosophers and physicists resist this conclusion. They point out that while relativity shows sentientality is observer-minus dependent, it doesn't necessarily prove all moments exist. Perhaps only the present exists, but which events constitute the present depends on the observer. Or perhaps the formalism of relativity is just a useful mathematical tool that doesn't reflect deep metaphysical truth about time's nature. The block universe theory also relates to quantum mechanics in interesting ways. In the many minus worlds interpretation, the block universe branches into multiple timelines at each quantum event. The future isn't a single timeline, but a vast branching structure of all possible outcomes. You might think of this as a bushel of loaves rather than a single loaf of bread, with each possible history corresponding to a different branch. Some physicists and philosophers have suggested that the passage of time might be related to the accumulation of quantum correlations and entanglement. As systems interact and become entangled, the universe's quantum state becomes more complex. This growing complexity might constitute an objective flow of time, even in a block universe framework. The past would be regions of spacetime with less quantum complexity, and the future regions with more. String theory and other approaches to quantum gravity might ultimately clarify the nature of time. Some string theorists have suggested that time might emerge from more fundamental, atemporal quantum structures. In this view, space-time itself, including time, isn't fundamental but arises from quantum entanglement and information in a network of quantum states. If this is correct, then the question of whether the block universe is real might be dissolved time as we experience it would be an emergent feature of a deeper reality that doesn't have time at all. The block universe theory also affects how we think about identity and persistence. If whole versions of you throughout your life exist equally in the block, what makes them all you? Is there a single persisting entity moving through time, or are you really a series of temporal slices, each existing at its own time coordinate, with the illusion of persistence created by psychological continuity and memory? Despite its strangeness, The block universe theory has become increasingly accepted among physicists familiar with relativity. It's the natural interpretation of the mathematics, even if it contradicts our intuitions. Whether it's the correct metaphysical picture remains debatable, but it represents one of the most striking examples of how physics can challenge our deepest assumptions about the nature of reality. Time travel has long captured human imagination from H.G. Wells' The Time Machine to countless science fiction stories. But is time travel possible according to the laws of physics, or does it remain forever in the realm of fantasy? Surprisingly, general relativity allows for solutions that include time travel to the past, though whether these solutions exist in nature and whether they permit actual time travel without paradox remains uncertain. The most famous possibility for time travel arises from closed time-like curved CTCS paths through spacetime that loop back on themselves in time. An observer following such a path would return to their own past. Several solutions to Einstein's equations contain CTCS, including rotating black holes described by the Kerr metric, traversable wormholes, and spacetimes with certain exotic matter distributions. Ica black hole, formed by a rotating star's collapse, has a different structure from an unminus rotating Schwarzschild black hole. Instead of a simple event horizon and central singularity, it has an inner and outer horizon, a ring singularity, and regions of spacetime that contain CS. In principle, an observer can enter such a black hole, navigate through its interior, and emerge from what's called a white hole into their own past or into another universe. However, practical and theoretical problems abound. The interior of a curved black hole is likely unstable. Small perturbations might cause it to collapse or transform into a Schwarzschild black hole without CTCS. Moreover, even if the geometry allows CTCS, actually following one without being destroyed by tidal forces or radiation is another matter entirely. And we don't know if white holes can exist in nature, or if they're merely mathematical curiosities. Wormholes present another possible route for time travel. A wormhole is a hypothetical tunnel connecting to distant regions of spacetime. If you could travel through a wormhole, you might emerge light minus years away or even in a different time. The physicist Kip Thorne and his colleagues showed that if a traversable wormhole exists, it could be converted into a time machine by moving one mouth at high speed relative to the other, using time dilation to create a time difference between the two mouths. But wormholes face severe obstacles. To remain open and traversable, a wormhole would need exotic matter with negative energy density to counteract the gravitational tendency to pinch it closed. While quantum field theory allows negative energy densities in certain limited circumstances like the Casimir effect, it's unclear whether enough exotic matter could be assembled to stabilize a macroscopic wormhole. Moreover, calculations suggest that a wormhole time machine might be destroyed by vacuum fluctuations and radiation feedback just as it's about to form CTCS. Even if time machines are possible, they raise the famous grandfather paradox. If you travel back in time and prevent your grandparents from meeting, you would never be born. So you couldn't have traveled back to prevent their meeting, so you would be born, and so on. This logical contradiction has led some physicists to propose various resolutions. One resolution is the Novikov self-consistency principle, proposed by physicist Igor Novikov. This principle states that local actions of time travelers must be self-consistent. They cannot create paradoxes. If you try to shoot your grandfather, your gun will jam, or you'll miss, or something else will intervene, ensuring consistency. The laws of physics conspire to prevent paradoxes. While this resolves logical contradictions, it seems to imply a strange sort of fate. Time travelers lose their free will in ways that prevent paradoxes. Another resolution comes from quantum mechanics and the many minus worlds interpretation. When you travel to the past, you create a branching timeline. In the branch you create, you prevent your grandparents meeting, so that you in that branch is never born. But you came from a different branch where you were born. This eliminates the paradox, but at the cost of suggesting that changing the past doesn't really change your past, it creates an alternate timeline. Some physicists, notably Stephen Hawking, have proposed a chronology protection conjecture. The laws of physics prevent the formation of CTCS except in regions of spacetime already containing them, like the interiors of black holes where observers can't survive to exploit them. Hawking suggested that quantum effects would create a feedback loop of radiation and energy near any forming CTC, destroying the time machine before it could be used. While not proven, this conjecture would explain why we don't see time travelers from the future. Another temporal paradox involves the thermodynamic arrow of time. We've seen that this arrow arises from the universe starting in a low minus entropy state. But why should the entropy be low in one temporal direction and high in the other? Some physicists have suggested that at the Big Crunch, if the universe eventually recollapses, entropy might reverse, decreasing toward the crunch. Observers near the crunch would experience time running in the opposite direction, with their future pointing toward the crunch and their past pointing toward the bang. This leads to a strange symmetry. Perhaps time has no overall direction. Maybe at the universe's temporal midpoint, entropy reaches a maximum, and on either side of this peak, entropy decreases, creating the temporal directions pointing away from the center toward the Big Bang and Big Crunch. Observers on either side would think they're moving from Big Bang to Big Crunch, but they'd be moving in opposite temporal directions. This scenario, while speculative, shows how our understanding of time's direction depends crucially on cosmology. Quantum mechanics introduces its own temporal puzzles. We've mentioned the measurement problem and entanglement. But there's also the question of retrocausality. Some interpretations of quantum mechanics, particularly the translational interpretation and the 2-state vector formalism, suggest that quantum events involve both forward and backward causation, with influences from the future affecting the present. The Wheeler delayed minus choice experiment seems to support this. In this experiment, a photon passes through a double slit, and the experimenter can choose whether to measure which slit it went through particle behavior or to observe interference wave behavior, even after the photon has passed the slits. The photon's behavior when passing the slits seems to depend on a measurement choice made later. However, this doesn't allow sending information to the past. The correlations only become apparent after the fact. Another puzzle is the psychological arrow of time. Not only do we remember the past and not the future, but our entire mental life seems oriented from past to future. We deliberate about future actions, not past ones. We regret past mistakes but not future ones. We can change the future but not the past. This asymmetry seems so fundamental to consciousness that it's hard to imagine experience without it. Yet, if the block universe theory is correct, past and future exist equally, so why does consciousness have this orientation? Some philosophers and cognitive scientists suggest that the psychological arrow emerges from the thermodynamic arrow. Our brains are physical systems that obey the second law of thermodynamics. Memory formation requires creating ordered structures, which can only happen in the direction of overall entropy increase. Thus, our mental orientation toward the future is ultimately grounded in thermodynamics, the special initial conditions of the universe. Causation itself becomes puzzling in light of modern physics. In classical physics, causation seemed clear: earlier events cause later events through deterministic laws. But relativity shows that temporal order can be observer minus dependent for space-like minus separated events. And quantum mechanics introduces indeterminacy, with some events like radioactive decay happening randomly without prior causes. How should we understand causation in this context? Some philosophers argue that causation should be understood not in terms of temporal priority, but in terms of counterfactual dependence. A causes B if, had A not occurred, B would not have occurred. Others suggest causation is ultimately about information flow or correlations. These debates show that our common minus sense notion of cause and effect, like our common minus sense notion of time, needs revision in light of modern physics. The mysteries surrounding time, its nature, its direction, the possibility of time travel, the relationship between time and causation remain among the deepest in all of science and philosophy. Each answer raises new questions. If we solve the grandfather paradox, we confront questions about determinism and free will. If we explain the arrow of time, we face questions about cosmology and initial conditions. If we unify relativity and quantum mechanics, we may find that time itself is emergent or elusive. The nature of time continues to challenge our understanding and invite new investigations. One of the greatest challenges in modern physics is to unify general relativity and quantum mechanics into a theory of quantum gravity. These two pillars of 20th-century physics are spectacularly successful in their domains. Relativity describes gravity, spacetime, and cosmology with remarkable accuracy, while quantum mechanics explains atoms, molecules, and fundamental particles. Yet they seem fundamentally incompatible, especially in their treatment of time, and neither can explain certain extreme situations like the Big Bang or black hole interiors. The need for quantum gravity becomes apparent in situations where both gravitational and quantum effects are important. Inside black holes, densities become enormous while sizes shrink to the quantum scale. At the Big Bang, the entire universe was compressed into a region smaller than an atom. In these regimes, we need a theory that incorporates both quantum mechanics' probabilistic nature and general relativity's curved spacetime. But attempts to simply combine the two theories run into severe difficulties. The core problem is that general relativity treats spacetime as a smooth, continuous manifold that curves in response to different energy. Quantum mechanics, however, deals with discrete particles and quantized energy levels. When we try to quantize gravity the way we quantized electromagnetism to create quantum electrodynamics, we get infinities that can't be removed. The theory is non-minus for normalness, meaning its predictions become meaningless at high energies. Moreover, the two theories treat time very differently, as we've seen. In quantum mechanics, time is an external parameter, a backdrop against which quantum states evolve. In general relativity, time is part of the dynamic spacetime fabric. How can we have a theory where time is both quantum and classical, both an operator and a parameter? Several approaches to quantum gravity have been developed, each with different implications for the nature of time. String theory, perhaps the most well-known, proposes that fundamental particles are not point-light but are tiny vibrating strings. Different vibration modes of these strings correspond to different particles. Gravity emerges from one particular vibration mode. String theory requires additional spatial dimensions. Beyond the three we experience typically 6 or 7 extra dimensions, making space-time 10 or 11 minus dimensional in total. These extra dimensions are assumed to be compactified, curled up so small we don't notice them. The theory is elegant and has many attractive mathematical properties. It unifies all forces and particles in a single framework and naturally includes gravity. However, string theory's implications for time are subtle and still debated. The theory treats time conventionally in many formulations, but some versions suggest time might have different properties in the full quantum regime. Moreover, string theory predicts a vast landscape of possible vacuum states, each corresponding to a different possible universe with different physical laws. This has led to anthropic reasoning. We observe our particular laws of physics, because only universes with such laws can support observers. Loop quantum gravity takes a different approach. Instead of adding extra dimensions or new fundamental objects, it directly quantizes space-time itself. In this theory, space is not continuous, but is woven from discrete loops or networks of quantum geometry. The minimum area and volume are not zero, but are quantized in units of the Planck scale. Space is granular at the smallest scales, like a fabric woven from threads rather than a continuous medium. Loop quantum gravity makes specific predictions about the quantum structure of spacetime. It suggests that the Big Bang singularity is replaced by a big bounce, where a previous contracting universe reaches a minimum size and then bounces into expansion. The singularity is avoided because quantum effects become strong enough at Planck- scale densities to halt the collapse. Time would continue through the bounce, though its nature might be very different in the quantum regime. In loop quantum gravity, time presents special challenges. When you write down the quantum version of Einstein's equations, the Wheeler-Dewitt equation, time disappears. The equation describes the quantum state of the entire universe, and it's timeless. There's no evolution in time because time itself is part of what's being described. How do we recover our experience of time from this timeless equation? One approach involves what's called the internal time or physical time formalism. The idea is that time emerges from correlations between different parts of the universe. Instead of absolute time, we have relational time. One part of the universe serves as a clock for the rest. Time is what clocks measure, and clocks are physical systems that change in regular ways. This might seem circular, but it suggests time is fundamentally about relationships between physical systems rather than being a container in which events occur. Another approach to quantum gravity is causal dynamical triangulation. This method builds spacetime from simple geometric building blocks, like triangles into dimensions or tetrahedron for dimensions, and uses computer simulations to explore which configurations are most probable. Remarkably, these simulations show that a 4-dimensional spacetime naturally emerges at large scales, even though the underlying building blocks don't prefer any particular number of dimensions. In causal dynamical triangulation, causality is built in from the start. The triangulations respect a causal structure, with some building blocks in the past of others. Time has a special role here, more fundamental than space. The emergent space-time has a clear time direction and behaves differently in temporal and spatial directions, which might explain why we experience time so differently from space. Some physicists have proposed that time might be emergent from something even more fundamental, not just relational time emerging from a timeless quantum state, but time itself arising from quantum entanglement or quantum information. The idea is that the flow of time, or at least our experience of it, is related to the accumulation of quantum correlations as systems interact and become entangled. This perspective is supported by a theorem in quantum mechanics showing that time evolution increases entanglement entropy in typical quantum systems. As the universe evolves, quantum systems become more entangled with their environments, creating an ever-growing web of correlations. This increasing entanglement might constitute an arrow of time at the quantum level, potentially related to the thermodynamic arrow. Moreover, recent work on the holographic principle, the ADS-CFT correspondence and string theory suggests deep connections between entanglement and space-time geometry. The holographic principle states that all the information contained in a volume of space can be encoded on its boundary, like a hologram. The SCF correspondence is a specific realization where quantum theory without gravity on a boundary is exactly equivalent to a theory with gravity in the interior. In this correspondence, spatial distances in the gravitational theory are related to entanglement entropy in the boundary quantum theory. More entanglement corresponds to shorter distances. This suggests that space itself might emerge from quantum entanglement. Some physicists, like Leonard Susskind and Juan Maldacena, have proposed that even wormholes might be understood as maximal entanglement between black holes EREPR. Connecting Einstein minus Rosen bridges wormholes with Einstein minus Podolsky minus Rosen entanglement. If space emerges from entanglement by time as well, this is an active area of research. Some proposals suggest that time's flow corresponds to the quantum computation performed by the universe, the ongoing process by which quantum information is processed and redistributed. In this view, time is not a fundamental dimension, but an emergent phenomenon related to information dynamics. Another intriguing approach comes from theories of quantum cosmology, particularly the proposals by James Hartle and Stephen Hawking. Their no-boundary proposal suggests that the universe's quantum state can be described by a path integral over all possible geometries. In this formulation, the Big Bang is not a singular beginning but a smooth, quantum event where the distinction between space and time breaks down. Imaginary time, a mathematical tool from quantum mechanics, replaces real time near the Big Bang, and the universe has no boundary in imaginary time. This proposal, if correct, would mean that asking what happened before the Big Bang is meaningless not because time began at the bang, but because the concept of before doesn't apply when time itself is treated quantum mechanically. It's analogous to asking what's north of the North Pole. The question assumes a framework northward direction that breaks down at the pole itself. The various approaches to quantum gravity disagree on many details, but they share a recognition that our classical intuitions about time break down at the Planck scale. Time might be discrete rather than continuous, emergent rather than fundamental, relational rather than absolute, or even illusory in some deep sense. What all these theories attempt is to provide a description that reduces to classical general relativity at large scales and quantum mechanics at low energies, while predicting new phenomena in the extreme regimes where both effects matter. One key question is whether quantum gravity will preserve determinism. Classical general relativity is deterministic given initial conditions and boundary conditions. The evolution is uniquely determined. Quantum mechanics introduces fundamental randomness in measurement outcomes, but the evolution of the wave function itself, the Schrödinger equation, is deterministic. Would quantum gravity maintain this structure, or might it introduce new sources of indeterminism? Some physicists speculate that quantum gravity might violate causality in subtle ways, perhaps allowing for microscopic violations of the chronology protection conjecture. Others suggest that quantum gravity might resolve the black hole information paradox, showing how information that falls into a black hole is eventually returned in Hawking radiation, preserving the deterministic evolution of quantum states. The unification of quantum mechanics and general relativity would have profound implications for our understanding of time. It might reveal that time is not fundamental but emergent from more basic, atemporal structures. Or it might show that time is a quantum structure, with minimal time intervals at the Planck scale. It might explain why time has an arrow connecting the cosmological thermodynamic and quantum arrows into a unified framework. Progress toward quantum gravity has been slower than physicists hoped when the quest began decades ago. The energies where quantum gravitational effects become important are far beyond what any conceivable particle accelerator could reach. The Planck energy is about 1019 GeV, compared to the Large Hadron Collider's maximum of about 14,000 GeV. This makes direct experimental tests extremely difficult. However, there are indirect ways to search for quantum gravity effects. Observations of the cosmic microwave background radiation might reveal imprints from quantum gravity effects in the early universe. Gravitational wave observations might detect signatures of quantum spacetime structure. Studies of black hole thermodynamics and information loss might provide clues. And mathematical consistency requirements might eventually determine which approach is correct, even without direct experiments. The quest for quantum gravity is ultimately a quest to understand the deepest level of physical reality, the level where space-time itself is quantum mechanical. At this level, the nature of time might be radically different from anything we experience or have yet imagined. Solving this puzzle will require not just new mathematics and new experiments, but perhaps fundamentally new concepts, new ways of thinking about existence and causality that go beyond our current frameworks. After our journey through special relativity, general relativity, thermodynamics, quantum mechanics, the block universe, time travel paradoxes, and quantum gravity, we return to our opening question: what is time? The answer we've discovered is far more complex and strange than we might have imagined. We've learned that time is not absolute, as Newton believed. Its relative different observers experience different rates of time flow depending on their motion and their location in a gravitational field. Time dilation is not a theoretical curiosity, but a measured phenomenon that must be accounted for in technologies like GPS. So observers can disagree about whether events are simultaneous, whether one event occurs before or after another, and how much time elapses between events. We've learned that time is not separate from space, but is intimately bound with it in a four-dimensional space-time continuum. Space and time are interchangeable in certain ways. What one observer sees as purely spatial separation, another sees as a mixture of space and time. The geometry of space-time can curve and warp, carrying time with it, slowing near massive objects and nearly stopping at black hole event horizons. We've learned that time has an arrow, a direction that distinguishes past from future. This arrow arises not from the fundamental laws of physics, which are largely time minus symmetric, but from the special initial conditions of our universe, the fact that the Big Bang began in an extraordinarily low minus entropy state. The universe has been evolving toward higher entropy ever since, and this evolution defines the direction we call future. Our ability to remember the past but not the future, to see eggs break but not spontaneously reassemble, all follows from this thermodynamic arrow. We've learned that time behaves strangely in the quantum realm. While quantum mechanics successfully describes how systems evolve over time, time itself is treated as an external parameter rather than a quantum observable. This asymmetry between time and other quantities might point to something fundamental about time's nature, or it might indicate that quantum mechanics is incomplete. Quantum entanglement seems to allow correlations that transcend time in puzzling ways, and quantum measurement might require special treatment of the present moment. We've encountered the block universe theory, which suggests that past, present, and future all exist equally in a four-dimensional structure. Our sense of time flowing, of the present moment being special, would in this view be a feature of consciousness rather than objective reality. This theory follows naturally from relativity's mathematics, but it conflicts with our deep intuitions about time and raises difficult questions about free will, causation, and the nature of existence. We've explored the possibilities and paradoxes of time travel, while general relativity allows solutions with closed time-like curves. Practical and theoretical obstacles make actual time travel uncertain. The grandfather paradox and its proposed resolutions from self-minus consistency principles to many minus worlds, quantum mechanics reveal deep puzzles about causation and the openness of the future. We've seen that unifying our theories of time from relativity and quantum mechanics remains one of physics' greatest challenges. Approaches like string theory, loop quantum gravity, and causal dynamical triangulation each offer different visions of how time might behave at the Planck scale. Some suggest time is emergent from more fundamental structures, arising from quantum entanglement or information dynamics, rather than being a basic feature of reality. So what is time really? Perhaps the most honest answer is that we don't fully know yet. We've found that a great del time is relative. It's part of space-time. It has an arrow, It's connected to entropy and causation, but fundamental questions remain. Is time fundamental or emergent? Is it continuous or discrete at the smallest scales? Does the present moment have objective reality, or is it merely a feature of consciousness? How do we reconcile quantum mechanics, external time, with general relativity's dynamical time? Can time travel exist without paradox? These questions aren't merely academic. Our understanding of time shapes how we think about ourselves and our place in the universe. If the block universe is correct, then all moments of our lives exist eternally in space-time. And in some sense we are four-minus dimensional beings stretched out in time rather than three-minus dimensional beings moving through it. If time is emergent from quantum information, then time's passage might be related to the ongoing quantum computation of the universe. The nature of time affects our understanding of free will and moral responsibility. If the future already exists in the block universe, are our choices predetermined? Or does the fact that there are choices arising from our deliberation and character preserve genuine agency even in a block universe? These are not just physics questions, but philosophical ones that touch on meaning, purpose, and human dignity. Time also connects to our mortality. We are temporal beings with finite lifespans, experiences that come and go, memories that fade. Understanding time's nature helps us understand our own nature. If time is an illusion and all moments exist eternally, perhaps death is not the end it seems, but merely a boundary in space-time. Or if time is fundamental and the present uniquely real, perhaps existence is more fleeting and precious than the block universe suggests. The study of time also reveals something important about science itself. Progress in understanding time has required us to question and revise our deepest intuitions. Common sense says time is absolute and universal, but relativity proves otherwise. Intuition says only the present exists, but relativity suggests otherwise. Our subjective experience of time flowing seems undeniable, yet the block universe theory challenges it. This willingness to follow evidence and logic beyond common sense, to test intuitions against observation, to accept counterintuitive conclusions when the mathematics and experiments demand them, is one of science's greatest strengths. The story of time is a story of how human reason can probe beyond surface appearances to discover deep truths about reality. Yet science doesn't have all the answers, at least not yet. The problem of time in quantum gravity, the question of time's fundamental nature, whether time is real or emergent, these remain open questions at the frontier of physics. The theories we have are incomplete, pointing toward a deeper understanding we haven't yet achieved. Future discoveries might revolutionize our understanding yet again. Perhaps experiments will detect signatures of quantum spacetime structure, vindicating one approach to quantum gravity over others. Perhaps theoretical breakthroughs will show how to unify relativity and quantum mechanics, revealing time's ultimate nature. Perhaps we'll discover that time is even stranger than we currently imagine, with properties we haven't yet conceived. Or perhaps some questions about time lie beyond physics, in the realm of philosophy or even mystery. Perhaps certain aspects of temporal experience, the qualitative feel of time passing, the sense of being in the present moment, the experience of agency and choice, can't be fully captured by physical theories. This wouldn't diminish physics achievements, but would recognize that the full story of time might require multiple perspectives: physics, philosophy, neuroscience, phenomenology. What we can say with confidence is that time is not what it seems. The intuitive, common-minded sense view of time as an absolute, universal, uniformly flowing medium is wrong. Time is relative, part of space-time, subject to curvature and dilation, perhaps emerging from more fundamental structures. The present moment is not universally defined. Sentientality as observer mind is dependent. The distinction between past, present, and future might not be as absolute as it appears. These discoveries are humbling and almost inspiring. They remind us that reality is stranger and more subtle than our everyday perceptions suggest. They show that the universe operates according to principles that can be understood through mathematics and experiment, but that often defy intuition. They reveal that questioning even our most basic assumptions, like the nature of time, can lead to profound insights. The nature of time remains one of the deepest mysteries in all of science. It connects to cosmology, quantum mechanics, thermodynamics, consciousness, and the fundamental structure of reality. Every answer raises new questions. Every theory that successfully explains some aspects of time leaves others puzzling. This is not a failure of science, but an indication of how rich and complex the problem is. As we look to the future, we can expect continued progress in understanding time. New gravitational wave observations will test general relativity in extreme conditions. Advances in quantum computing might reveal new aspects of quantum time. Cosmological observations will probe the universe's earliest moments when quantum gravity effects were important. Theoretical work will continue to explore how to unify our different theories of time into a coherent framework. But beyond these technical advances, the study of time invites us to contemplate fundamental questions about existence. Why is there time at all? Why does it have the structure it does? Why can't we travel freely in time as we can in space? What is the relationship between physical time and experienced time? These questions connect physics to philosophy, science to human experience, equations to meaning. In the end, time remains both familiar and mysterious, intimate and alien, understood and puzzling. We live in time, we're shaped by time, yet time's ultimate nature eludes us. This combination of familiarity and mystery makes time one of the most fascinating subjects in all of science and philosophy. The journey to understand time is far from over, but what we've learned so far reveals a universe more remarkable than we could have imagined. Time, that most ordinary aspect of existence, turns out to be one of the deepest windows into the nature of reality itself. Time is the ultimate frontier. It is the dimension that allows for causality, for growth, and for the very consciousness that allows us to ask these questions. As we fade to black, remember that in the 4-dimensional block, no moment is ever truly lost. Every sunset over Istanbul, every calculation made in a Zekria KOY alley, and every word of this 15,000-word journey exists forever. We are not just drifting in time, we are the very fabric of it.